Hi and good afternoon everybody. Many thanks for coming along today. Today we are talking about portal frames and we're talking about using MasterPort Plus plus some additional tools to get the most out of your portal frame design. I'm going to start the MasterSeries and come straight into MasterSeries 2018, which we released about 3-4 weeks ago. And uptake has been very good, and the response back has been also very good. So as you can see, we can do frames, portal frames, we can do connections, slabs, timber, flat slabs, masonry, retaining walls. The MasterSeries is a fully encompassing suite of programs. But because it's modular, that allows us to pick and choose what we require at this moment in time. So you don't buy everything, you buy only what you need, not what you don't need. So I'm going to go into portals and into MasterPort. And I'm going to do a frame similar to this one. And we will hopefully walk through the full design. But before that, I'm going to take a brand new file. Demo 123 and create this as a brand new file. And we're going to look at all the different features and facilities that we have in MasterPort. So there appears to be something set as grade 36 in the default rather than 355, and I'll just check that out in a minute. So I'll just check that. So that's 355. That's 355. Okay, we'll just keep an eye on that. So we're going to work to EC3. And we are going to pin our bases, but in the service and sway stability loading cases we will use 20 and 10% loading. We will optimize our haunches. For our haunches, we're just going to deduct the flange off those to get as much as we can out of the depth with an assumed 20mm plate. Dead load, I'm a great believer in putting in this lower 0.25 and then adding in a service load so that when you're doing the dead plus wind uplift, you're not including the surfaces in case they're not there. It is a more significant problem in reversal when you don't have your services on board. And of course, we'll add in the self weight of the structure. We'll put in all the loading cases, including serviceability, so we can do our full foundation design. And once we've got the thing organized, we will also suspend all non-critical loading cases. And of course, we're going to look for the elastic critical load factor. So that's the first thing we're going to do. And you can see it's one span, put it in the front cube view. And if I now work through onto the spans, I'm going to change this to being 2 spans. So you only see 1 span here because we have this thing called global and in-bay symmetry. So when I turn off the global symmetry, I now get 2 spans. So I'm going to make the first one 24 meters and I'm going to make the second one 30 meters. So we can see they are now different spans. I'm going to make the rise only about 6.5 degrees on the rafter. So putting the wee asterisk or star tells it that it is an angle rather than meters. As you'll see down here is a little tool tip if you read that carefully, and as I hover you get different tips, of course you do, and it says use the star for degrees and the slash for 1 in. So my second portal I'm going to say 1 in 10. So sort of similar, not quite the same. Now, different spans, different haunch lengths. So I'm going to go for a 2.5 meter haunch on the short span, but I will go for a 3 meter haunch on the long span. So as we can see, we've got some default sections, and these are the inputs for the apex haunches. So 1 meter long and 2 times the standard depth. We can also ask to say, yes, we want a mono pitch, put a big Y in there, and or we could say we want a mansard, and we put in the length of the mansard, so a 6 meter mansard at the top if we so wanted, but we're not going to go that complicated here today. And naturally the mono pitch can be from the left or the right. So that's my spans done. So I'm now moving across to my columns. So the default height is 7. I'm going to keep it 7, and I'm going to make the next column 7. But then what I'm going to do is I'm going to raise up the right hand side of this column. So it's 7, but then it grows by 3 meters. So 7 plus 3 is 10. So 7 on this side, 10 on this side. And of course this will also be 10. This is going to be unrestrained over quite a bit of its length, but I'm still going to use a standard section, and I'll just keep those there. I'm just going to make this one a 533 as my default as well for the outer one, 533 by 82, and close. Oops, the grade is the wrong grade. Just be careful. 355 and close. The base levels, if we wanted to, we could turn around and say that this one is at a base level of 2 meters and lift it up, or in fact even -2 and drop that down, so we can cater for uneven bases. And likewise we can change the base fixity, but we're going to control the base fixity externally as being 0, 10, 20. Parapets, if I wanted a parapet of 1 meter or 2 meters on either of them, I can put them on, and because I've got the symmetry turned on, I'm going to have it in both, but I'm taking it out. That's very straightforward. Excuse me. Now what I'm going to do is I'm going to add in a lean-to. So I'm going to add in a lean-to. It's given me 2. So I now go to the new tab. As I add things down here, I get new tabs, so it tries to keep it as clean as possible. So I'm going to say no, I'm going to have only a lean-to on the right and take off the left lean-to. I'm going to kill those haunches and make it simply support it in a minute. 8 meters is fine. The rise is 1 and 8. That sounds okay. The top's at 4 meters. Let's pull that down to 3.5 meters, so it's a wee bit lower. And the column section, I'm going to start off with something quite light, probably a 254 by 31, and I'll probably, oh, there's my grades again not picking up. I need to pay closer attention. And then when I come to this one, I'm going to change this to be 355, and again I'm going to initially put in that 254 by 31 and close. So that's my smaller sections. Scrolling down through this, very simply, base fixity I'll let it do the same. Dead load I'll leave as the same as the others. Outer fixity and inner fixity is going to be 0 and 0 because it's going to be a beam and post, which means I don't want any haunch at either end. So I'm going to make this haunch length and make this 0, make that 0, and haunch length. So beam and post, just need to get rid of the wee silly parapet, don't really want that, and parapet is going to be 0. So very simple beam and post arrangement for my lean-to with a big proper portal in here. So that's my lean-tos. What have I got left if I was playing around? If I was playing around, I can have canopies, nasty little beasts. And again, I can, if I get a new tab called canopies, and I can play around with whether I want a left or a right. So I could leave just the left canopy and change the dimensions, thank you very much, but I don't really want a canopy. I'm going to turn off canopies. Back to my spans. I can also add in a mezzanine floor. So if I wanted to, I could add a mezzanine floor. And let's temporarily put one in, and then we're going to take it back out again because I want to just keep this clean and simple for you all to follow. So my mezzanine floor is going to be not on span 1, but it's going to be at 3.5 meters on span 2. So once I add in a mezzanine floor, I would need to add in some supporting columns because these aren't just for props. So now I've got props, and I'm going to tell them they're not in span 1 but in span 2, not 22 but 2, and I'm going to tell them they're at 5 and 10 meters. So if we go to the mezzanine floor, we'll see that we've actually told it not to include that. So there we go, put it back in, and we can add another column, and we can put on their own dead and live loads and whether they're pinned or fixed as well. Very complicated, very simple to use on a bay by bay basis for the mezzanine floor. So I'm going to drop out those mezzanine. So the mezzanine have dropped out, so it assumes they're props. Come back to my props and turn off those props. Don't mistake props for gable posts. They're totally different. Okay, where have we got to? We've put our mezzanine floors in, and we've got the ability to also add in crane loads if we so desire. And when we go to cranes, you'll see that you're actually putting in your horizontal and vertical eccentricity, because they will actually generate a moment into the column either due to weight or surge, plus your crapping, self weight, all the standard input that you would require for a crane. And we can put 2 cranes on if you so desire, but I'm not going to put the cranes on. Keep it nice and simple and clean. Okay, so that's my simple plain frame, but I don't have any wind load on it. And before I can do wind load, I really want to create a 3-dimensional frame. So let's go into 3D. And here we go, some little mishmash and assumptions that we'll fix in a minute. But in 3D, we automatically also get gables and bracing now that we're in 3D. I'm going to say that I have 8 bays, and the spacing is going to be 6.25 between bays. So they're all 6.25, and of course you could turn around and say that you have non-equal spacings. So I could say an unequal spacing of 4. So that's 4, and then another 8 bays at 6.25. So if you had to have a makeup because of the site size, you can have a different set of spacings between your columns and bays. The current portal I'm going to make 1, 2, 3, 4. So that's the 4 portal we're going to use for design. Actual depths we don't need to worry about, because that's really only when we're not dealing with physical wind loading and grid lines and things like that. We're not going to worry about and stuff like that. We can change around some of the data, but we're not going to. So what I'm now going to do is go to my gable posts. So here we go. 3 sets of posts, and remember we still have this thing called in span symmetry. If I turn that off, you'd see that we'd only get 3. So what I'm going to do is I'm going to put them at 6 and 12 meters, take out the middle one, and I have them at 6 meter centers. I'm now going to add in some more posts into the other bay, and I'm going to say it's going to be span 2. And for simplicity, I will sort of half mimic that with 7.5 meter and 15 meter gable posts. So we now need to change our bracing to match that. And the other interesting thing is I haven't actually set a section size yet. So I think I'll go for a 355, and I will probably go again for my favorite starting section because it's nice and stable, is a 146 wide and 254 and close. So let's put those on. So, and as you can notice, as I click on a member, I'm taken directly to its editing point. So there we go. I'm at the first one, there I'm at the second one, and it's very straightforward. So if I wanted to go to my wind bracing, I can just click on any of the wind bracing and I'm taken there. So at the minute it's thinking it's got 6 panels in the bracing. I'm going to say 4. So we've now got 4s. And we've also got this little brace member here. And this little brace member is really to do with transmitting load, A, from the column into the bracing, but also, and it's going to be a transfer beam, and we're going to say no. So it's not really going to be a beam in here, it's just going to be mimicking the purlins so that we share the load between the two ends. Coming down to my lean-tos, I could say that I only want 1 brace in here, or I could say 2, keep it nice and neat. Not that it does much difference, it's just going to be a shorter angle. And mezzanine beams, I don't have anything. So that's my bracing done. Now the only one I have a little problem with is looking at the wall bracing. So that is a single. These are doubles, and that's a double there. So a double here makes sense, nice and neat. But for this here rise, it does not look nice. So what I'm going to do is I am going to break this link that makes all the bracing automatic. And then I'm going to go, actually put it back in again for a second. Yeah. I'm going to go to this set, and for the externals I'm going to go for 3 legs. 1, 2, 3, because I'll need them. And for the internals I'll also go for 3 legs because I'm going to need those in a second. 3 legs. Now if I break this, I can change this geometry. So I could take these two and make them connect here. So if I take this and I change its height from 3.3 up to about 4.5, well, why not ask the program what the height is, and if I come in and say y coordinates, it's actually at 4.5 exactly. That's good. And then the next one is coming in at 4.5. So there, those two are now matching properly. And I could lift the two ends here to make them equally pitched, but I'm just going to leave that as it was because I'm not that worried. So over here, I need on this side to lift this column brace, and it needs to be on the y-axis at 7 meters. So make this 7 and make this 7, and then you could make these pair to be 3.5s. Just so we have that control that we don't have to be fully automated in everything that we do. We can override the automated processes and make things a lot easier. So there we go, and we now have no contradictions. So that's my 3D frame created. Now we're going to think about the loading, and it's the wind and snow load. So I'm now going to add in the wind and snow. So let's go to snow first, and we can see we're going to go for 0.5 at 100 meters above. So I'm going to just note that, come to wind, and in the wind I can put in the basic Q values, the wind pressures that I'm going to assume, and then let this put all the internal external suctions and go and do it all. Or I can use the site data from Master Key Wind, and in there, let's go and choose a location, and I can run along and I can choose a grid here and say, oh, that looks to be roughly somewhere down there. Is it over there? There's Birmingham, and we can say, right, we're just about there. Close enough, and it's lucky. Or I can say, let's go to Birmingham, and I was right, that was Birmingham, and then I can say I'm just to the south of Birmingham. And most times it's probably accurate enough, to be honest, unless you're in a real pickle and want to get it right down to the bone. But we can do that. We can get down to the bone, because if I pop up my Chrome, I can go to a website called gridreferencefinder.com, and I've gone to somewhere called Bromsgrove, just to the right, I believe, of Birmingham, and I can say, right, we're actually going to be putting a nice portal frame on the edge of the Gulf Centre. So there it is. I'm going to locate it there, and there is my grid reference. Copy and paste that back to MasterPort, paste that in, press enter, and there it goes, just to the bottom left. I thought it was the right, it's the bottom left of Birmingham is Bromsgrove, and I'm going to lock that in. So that's locked in, and there's my wind pressures. But what I need to do is to tell it where the wind blows onto the structure. If I wanted to blow on with the north over here on the structure, we then need to rotate this by, say, 60 degrees and then have the wind blowing there. So that's giving us the dominant wind there on the structure. And luckily for me, Bromsgrove's reasonably well sheltered in the middle of the country. So that's my wind analysis done. I come out of that, exit from the wind, and it's updated all these values and put them on. Now, what I didn't do, and I should have when I was in here, it was just make a note, what is the real altitude? And the altitude is 127 meters, which is interesting. So we're probably still going to be down that pretty quiet zone, but we just would be better to update in the snow our altitude to be 1.27 or 127 meters and no returns. So what's left to do? Well, probably what's left to do is to look at these and see what they give you. So first of all, if I look at the frame in 3D and we put some color onto it, we can see our lovely frame with our eaves ties, our bracing, and we can see that we're assuming we need to put that tie in there. We've missed that when we look at it in 3D. So easily add in an additional brace at that point and at that point to make those work. So, and I'm going to take this one, because the others were just the transfer members from one end to the other. I really do want to actually have a proper brace member in here. So it's roof brace. I'm going to come down to here and I'm going to go insert, and I don't need to tell it anything other than it's from 6 to 6, in this case 6 meters to 6 meters. There we go, and it puts those in. And then I'll come down to this set here, and I'm going to come and put my cursor in here, insert another, and it's going to be at 7.5 and 7.5, 7.5 and 7.5. We could have swapped the bracing around to go the opposite direction, but we would have then had the problem we would have needed to put a brace in here, which is a bit more nasty, to try and stabilize that central gable post here. And I don't fancy putting a bracing member in there. Just let the purlins look after that. So that's your lovely 3D structure coming in beautiful detail as to how it's working. We're assuming we're putting channels in there for the time being. We can change those at any stage during the design. Now, what we've also got is the wind loading on the structure. So here we go. You sort of turn off that color section, and we can now see coming along in that direction what the CP values were, but more importantly, what is the Q value? So we're taking the pressure, so it's going to be 3.34 on the leading face and 0.66 on the leading edge. So not that high a degree of wind pressure on this structure, except for in these wee corners, but it does reduce itself very, very quickly as we go inside the structure as well. So that's in one direction. Obviously the next direction is the same, but with the alternate rafter load, which is very weird, but that's the way the codes decide to do it. And then we have the gable end. And then because our frame is asymmetrical, with asymmetrical wind, it does it all again in the other directions, as you can imagine. And then as well as that, because I asked for internal pressure and internal suction, we have the same with internal pressure. So we've gone down here, but up here. So that pressure internally is reducing this value, but increasing this value. And we can go through and look at all of those as well. And then the suction case, where it's increasing this one and decreasing that one because of suction in the building. So that is your wind. Very, 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 very fancy. And then because we have snow, we have a little snowflake. And there we get our basic loading. And then we can look at the L2 loads. And the L3 is your snow drift, interestingly. It's looking that drifting is actually going to come out along here. And then you have L4 if it exists, which it doesn't, and L5 if it exists, which is a slightly different drifting of the structure. Obviously the slope here is quite shallow, so therefore it's saying we could have drifting on that surface, which I think is quite interesting. So those are all your loading cases. That is all your frames. That's half an hour spent. We're going to go through now and let us work through the design. So first things first, analyze it. And as a rule, I like to start off with an elastic design. I just think let's not mess around with the wrong section sizes doing a plastic analysis. Let's get in with an elastic, see where we have to go from that, and then start designing. So it's doing 160 loading cases because we got 6 wind directions times internal pressure and internal suction times dead and live or dead only. So and it's Eurocode, so we actually have quite a lot of loading cases that it's going to work through. Now the other thing is I told it to optimize the cases, so it will at some stage when I keep going through my iterations say, well actually that one's not doing anything, let's think it's not used in any design checks, let's take it out. It's not critical. So output, graphical, only thing that counts. And of course you want to just check that it looks sensible. This is where I find that people are quite amazed. If we look at just this half of the portal down here, and it's probably easier to see it here, you will notice that these hinged areas have similar hugging moments, but the first bay in doesn't, because it's working as a half-tide portal from this diagonal here is tying it back into this tide frame. So you always find that you do get a slightly lower set of values on this first one, and that also means that the differential and deflections are more gradual between these big deflections horizontally to these smaller to virtually nothing in here. So if I was to look at values, Um, those are the beam. Oh yes, the values are written on the member. So 440 there, down to 300 here. So just scrolling in, is 440 here and here, down to 300 down here, and then down to a very small 46, as you'd expect. And the others are 440, 443, just that tiny, tiny wee bit extra relaxation as everything goes. So that's that. If we look at our deflections, and I'll just turn off those, we will see how the frame is currently behaving, and this is with the magnification. So let's put it in the front. You can see the moving out as you'd expect, the rotation, but not as bad here, quite bad here. And when we put it in the plan, you will see, as I was saying, this first bay isn't moving anywhere near as much as the other bays. And if I actually ask it to give me the X displacements, you'll see that these are all around 49, whereas this is only 15 and then down to 8. So there's a drop off there that's quite significant, but that was, bear in mind, ultimate. So let's go in and just do some design. Design, steel design. And here we go. It's showing us our frame. It's showing us what this grey is actually all 196, well, excluding the what's the word for it? Excluding the service cases. And then you have your other rafter, and you have your column here with the wee chunky, and oh, that columns need to go on and go up. It's look overstressed by 90%. And this one's looking good, and that one's looking good. So let's just go and say size as a plastic, lightest frame with normal average restraints. There is to be seen, and we now go auto size. And to speed things up, we're not going to analyze the full 3D frame. We're going to do that on this one bay first. So we're initially trying to get an elastic frame, and then we're going to try and push the boundaries on those members. Still taking a while because I asked for internal pressure and suction. Just, as I say, tripled my loading. So we're in the second stage where we're starting to form the hinges. And now we're going to do the plastic analysis, and it's going to do the full analysis on the rafters, and then do the full 3D analysis. Okay, while we're looking, any questions? Can you apply user define? Yes, you can. If you didn't go in to the Win program, you had the option to put in your own Q values for each direction, which is the simplest way to do it, and it works very, very effectively. Does the snow work out snow drift? Adam, actually we just did that and I showed you. So what have we got? We got 5 plastic hinges and all these different loading cases, and I can kind of figure out where they're going to be, but just in case, yes, there's where we're going to have those plastic hinges. Okay, so we've done the big 3D analysis and we're now happy. What we now want to do is to check our sway stability. Our sway stability, our lambda crit, is all above 10, so we're all happy. No P delta was done, but we could add P delta, and it's all fine and hunky-dory. So now we will go and do the detailed design. So what we're looking at here was, we're going to say 1400 purlins, auto restrain the sheeting rails, and we will find it's not doing the one, it's doing all of these here and checking for the worst in all of those, and we'll see that we're getting away with these 1400 centers. If we check again for the appendix G, or appendix BB as it's called in the Eurocode, and we will see that we need to have at least one more stay down the column before it works. Looking at the next rafter, it all fails, and that's because I haven't done my stays, and they will be at 1800, and I'll go and do those. And it's doing both of these rafters because they've been asked to be the same section size. So it's going to assume the same restraint, which will probably put a wee bit of onus on it because the moments will be different from each side because of the column in here. And you can see it's running through a horrendous amount of checks, and it's finding that everything can work at 1800, and then the wee makeup out here. But what about the appendix BB? It's saying, oh, we need to stay there. So looking here, I'm going to take this off. Oh, I need to stay. So if I put that there, what about out to there? And it says, no, we still need to stay. So let's just put it here at the normal place and everything else is fine. And let's then just look at the other rafter, and it's going to be the same. The column, we just need to restrain that again. And interestingly, this column is overstressed, but that's only because we've gone past the point of the underside of the hunch. When we come into the restraints and auto restrain, we should actually drop off before that point. And I'm finding, in fact, it's thinking that it's unrestrained over its full length. So I could come in and say, no, 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 I actually want equal spacings. So it's going to have sheeting rails of some sort up the leg, and everything is now happy. Or I could say, what's the lower height? It was 7 meters, I believe. Just check, 7 meters. I can say, well, starting at 7 meters, so we have the first portion clear. So we have a big long portion and then the others. Or you could say starting at 0, and the first one is 7 meters, and then have the others coming in, and you'll see everything is fine. So then coming along and looking at the appendix G, and we're going to need to put a stay in here, and we'll see that we're just overstressing this, and so we just probably need, because it's looking at this overall length, I'm going to put another stay in there, and now it's happy, and the rest doesn't have much moment on it because it all comes back through to the other rafter. So again, we haven't done our restraints. Auto restrain at 1800, please. And we'll see that it's getting very close to being a failure down here, more than anything. So very nearly finished in 10 minutes, that main frame design. And yes, it is 1% on an axial with moment. I would propose tightening that one up and making that a bit tighter to make that work. So it would just request you starting here and putting in this one at 1.8, 1.7, and that's fine. And then just looking at our appendix G, which is done and it looks fine. Other rafter will be the same, and then you're coming to your last column, and we're beginning to fly. Again, it's a question of where the restraints are and where the purlins are, and we're assuming 1400 the whole way up, and it will auto restrain and put it down there. Get the shooting rail just at this point, and everything should be fine. And we are looking at the flexion problem. So it's saying that that rafter is deflecting a wee bit, but that obviously depends on how you classify the deflection. And it's looking at a dead plus live more than likely at a 1 over 360. So if I went into the axial with moment and changed my deflection limit from here being 1 3 over 360 to only 360 in live and 250 in dead, and I'm going to put in, I'll just leave that at that, change that to type 1, and now it's not a problem. And then finally, simply supported. It's not happy. The deflection's too much. So 1 over 360, I'm going to make that type 1 again. And it still is deflecting too much. So it's the deflection. So I'm going to have to take some manual action here. They never like that section. On the 28, I don't like the 102 flange. So I'm going to go, that's respectable. I much prefer that as a section. Shape, I'm going to accept that. And then I'm going to have to check the Appendix G. And it's showing that in reversal there's not a problem for the minimum dead plus light plus wind suction. And then finally this little beastie here, which is really not got anything on it worth talking about, and it's fine. So that's my main frame done. Happy days. Doing fantastic, believe it or not. Let's look at our bracing. So you just click on your bracing and you will see that I'm going to go for a grade 355 CHS auto size, and I'm going to actually ask it to auto size all of those braces in one go, so all my wall braces are going to be optimized now. So what we're actually seeing here is that we separate your design into your main frame, any secondary steel, any roof bracing, wall bracing, gable posts, and then if you have north and south members. So very quickly you will see that we're getting down to quite a small 88.9, and the channel is that we're putting in is 200 by 75 PFC. We'll leave that for fabrication and for your guttering and things, rather than changing to a hollow section. Down here this is a PFC, but I'm quite certain that that could very easily be a CHS. Move it up slightly. CHS, not a 600, don't think that would be needed, but just size that one member and it checks for the whole length, and we find we need a 76 by 2.5, too thin for my liking. A 76 by 3 will be more than satisfactory. And then we look at the roof, and again we can just ask it to auto size them all individually. Off it goes very quickly. And we'll see that we're actually getting 139s in the roof. We're actually getting 193s here, but in fact if you look at these, they are grade 2270. I should have been 350. Make this one 350 and then auto size again, and we should find they come down a wee bit lighter for us. So bracing, yeah, 114s, that's good. Still needs, because it's got quite a long length on it, but we'll work with that. Finally, gable posts, and this is probably the worst of all the gable posts. Deflection's a real killer here. Axial moment, going to set myself to the smart deflection limits, and we're going to see what we're looking at. So it's the wind. The wind is still working at 1 over 360. So we're going to improve our deflections. What is our lateral spacings? 1.4. So if we need to improve deflection, no messing around, we do need a heavier section. The 102 flange is not good enough, and that is a bit narrow. I'm going to be a lot happier with the 140 wide, and the reason for that is because it has to then check an torsional restraints on this, because it's going to say no, I do not like this unrestrained in reversal, so I'm going to have to put some stays on. And could I get away with a stay in the middle? No. So we're going to look at 2 stays. So how long can I get away with, and could I get away with a stay there? And let's see what this is like, and that's not happy. So let's put it there. That's happy. would this portion work without the stay? Yes. So bang, bang, bang. 3 stays required. Now, obviously, if we had walls coming up the structure, we would actually just start at the 4 meters up, at the 2 meters up, and have it fully restrained underneath that. So that is all our frame done. From a design point of view, we will reanalyze the whole frame. So if I come back to here, I am going to have to just ask it to redo a plastic design, ensure that everything is coming through, and I see actually that I had a grade 275. I wasn't paying attention from one of my columns, but that's fine. You're actually finding, I find with clients these days, that plasticity isn't the problem, it's deflections. If you have a 355 grades, then you can have problems with deflections because the stronger grade does nothing for your deflections. You're using lighter steel. So let's just go on out of that and save that. And now look at what we've got left. What we've got left to do in 10 minutes is connections. So let's go and work some magic. I'm going to accept that it is in general yep, that's okay. It's a portal, that's the one I was looking for, and my welds are standard weld sizes, and I'm going to say close, and it's now going to ask me what's your first joint. My first joint is going to be an eaves at that point. So here we go, very simply taking all the forces straight out of the analysis, and you will see that we've got a compression failure immediately. So the little symbol tells me I have a failure. I'm at 204% overstress because we want to be below 1 with all of these lovely values. So first thing I do is main stiffeners, and I'm going to put a bottom stiffener in of 10 mil and enter. So now I'm down to only 102% overstressed. I need more bolts. Very simply, bolts, and I'm going to go for adding in bolts. So now we've got more bolts, but when I add a third row, it's going to alleviate that weld problem. And there we go, 3 rows of bolts, and it works. But because the connections is such a horrendously complicated thing, it is doing one loading case at a time. It just would not make sense to try and even tell you where the failures are on 90 something cases in one go. So what I now want to do is either walk through the different loading cases manually, or just say go on, you find the next case. So here we have another case which is giving us a weld capacity problem with the 3 rows of bolts. So solution to that is really, and you would probably consider that anyway, going up to the top weld being an 8 mil weld, and that's happy. So let's scan again, and we're going to go into reversal, and it's fine. So this joint is perfectly good. I personally would like another row of bolts in the bottom. You never know when you're going to need it, and it just looks right. So I'm going to add another row of bolts, and that's my eaves connection done in 2 minutes. I'm going to add in an apex connection, or a beam to beam, and I'm going to do it here. And what I'm going to do first of all is give it a wee bit of a guide by lifting this bottom row up to say 100 mil. That just allows it to fit. I was getting a warning because the bolt wouldn't allow presentation. It would actually hit the flange when it was trying to go in. And that works, but it doesn't necessarily work for all loading cases. In this case, maybe it does, but I would probably pop 2 more rows of bolts in, one top, one bottom, to make it look a lot more robust for us. And then finally, the last joint I want to do is going to be a base plate, and I'm going to say OK. So beautifully, I will probably take this base plate here, and here we go. Excuse me. And it thinks everything is fine. Let's scan for failures. And believe it or not, it is fine. I have the time. I'm going to do another joint. I'm going to take another eaves joint. This time I'm going to do it over on this side. But this time, what I'm going to do is ask the program to try and come up with the solution itself. So auto design, it's going to run through and do all the design checks for all the loading cases and drop through them twice and make sure it doesn't cause any problems on the second iteration. And there we go, it's all done. And that, for this longer span, is the optimum design. Now it leaves the end of haunch weld as the default, same as the depth of the flange, but that is one of the welds that for our fabricators we can come along and say, well, actually I would be quite happy with an 8mm weld here, and it's saying no. Why is it saying no? Well, it's saying no because it assumes that both the haunch end and the haunch web weld have to carry at least 75% each, just to make sure. So we need a bigger weld on the end of the haunch, 10mm, and obviously the default 6mm on that, and that is my connection designed. Finally, I'm going to go through and design my concrete base plates. So base plate rules, going to have no uplift. I'm going to assume that the columns are tied into the slabs, so we're not going to have a problem with shear. And we'll ignore service moments. And we're going to go for a C3240 concrete, safe working pressure 200, and everything else is as normal. We'll consider no K passive, not that we need to, because we're not going to be considering shear anyway. And I'm going to say oh. So here we go, we can see that we're a 2250 square pad, and we've got top and bottom reinforcement mainly because we want to ensure that the shear on the base plates is quite good. We could turn off the top reinforcement if you so desired. I can come here, drop that down to zeros. So when I reduce it, it gets a wee bit annoyed thinking that we need to satisfy the minimum, but with no reinforcement we're all okay. But our base plates, if they're relying on the base to resist shear, you would need to have reinforcement. It's not something I talked about, but if you need to have shear bearing onto your concrete bolts on the concrete, putting in that top reinforcement is going to increase your shear capacity, your bearing capacity considerably by 3 or 4-fold and make it work properly. So there's all my pads, and obviously the bigger ones are in the inside. If I was just to put this in top view, we can look at this very nice and see, and that is what you would consider to be a sensible arrangement of pads on your structure. And all done. What we can do lastly on our pads is obviously we could have exported our connections to get us a DXF file of all our drawings. We can also do that for our pad foundations, and we can export the schedule to match. So if I'm going to do that, and I'm going to put them all out to 8666 and schedule, and it's going to fire up a little schedule. They're going to be very, very primitive because they will assume square pads unless we get fancy. So the rebar is going to be a single bar, until we need to have different bar diameters top and bottom. But the nice thing is we can get what is the weight, and we used a total of 7.4 tons. So there you go. We don't even need a quantity surveyor. Of course, we do have also the frame statistics, which is for the main structure, and that's going to tell you that we have 65.6 tons of steel in the project. Now, what it is going to assume is that all members come to the center line, so there is that tiny wee bit of overlap, but it is still a very, very good starting point for estimation purposes. So just looking through, that's me concluded my portal design in the 1 hour, exactly on time. Quite proud of that. We have three ways you can do portals, and I have been using this big thing called MasterPort Plus, where we can do 3D analysis of portals. It will do the basic wind and snow loading just from values you input and apply them, but I added in the wind analysis, and I added in the moment connections and the pad foundations. So I was using 1, 2, 3, 4 programs. And this is our Rolls-Royce way of intelligently designing a whole portal frame in an hour. If you want to step back and go small scale, you can work with 2D frames, and you would just need to use master frame with the simple MasterPort, or sometimes they call it MasterPort Lite, and steel sections, and this comes in at a considerably lesser cost than the big 3D version, as you can imagine. The third way of doing that is to look at the PowerPad solution. And PowerPad has a built-in 3-span version of the 2D, so we can do 3-span portals, no problems whatsoever. We also do have connections in the PowerPad version, but it's limited to only connections of up to 300 kilonewton meters. So if you're doing large span, 20-30 meter portals, you would want to upgrade to the full version, which if you do it within 60 days comes at a very, very considerable price. So if anybody does want a costing on the different options of MasterPort for your country, just drop me an email, tommy@masterseries.com, and I'll be more than happy to help you. So it only goes to say thank you very, very much.